calculate the AIC rating for a panel starting at the transformer, one must follow a series of steps. Firstly, determine the transformer's rating. This involves obtaining the kilovolt-ampere rating of the transformer supplying the panel. Secondly, calculate the base current. The formula for base current, denoted as I, is equal to the kilovolt-ampere rating divided by the square root of 3 multiplied by the primary voltage. The primary voltage is often 480 volts or 240 volts. Thirdly, determine the maximum short circuit current (SCC). To do this, one needs the short circuit current at the primary of the transformer, measured in kiloamps, the transformer impedance expressed as a percentage, and the primary voltage, denoted as V. Calculate the short circuit current at the primary using the formula SCC equals SCC multiplied by IP. Fourthly, convert the primary short circuit current to the secondary short circuit current. This is done by dividing the short circuit current by the transformer turns ratio, denoted as TR. The transformer turns ratio is equal to the secondary voltage divided by the primary voltage. Fifthly, calculate the panel AIC rating. This is equal to the secondary short circuit current divided by the panel safety factor. The panel safety factor is typically 1.25. Let's consider an example. Given a transformer rating of 250 kilovolt amperes, a primary voltage of 480 volts, a transformer impedance of 5%, a transformer short circuit current of 15 kiloamps, and a panel safety factor of 1.25, the calculations would proceed as follows. 1. Base current is calculated as 250 kilovolt amperes divided by the square root of 3 multiplied by 480 volts, which equals 300 amps. 2. Primary short circuit current is calculated as 15 kiloamps multiplied by 300 amps, which equals 4,500 kiloamps. 3. Secondary short circuit current is calculated as 4,500 kiloamps divided by 480 volts divided by 240 volts, which equals 2250 kiloamps. 4. The panel AIC rating is calculated as 2250 kiloamps divided by 1.25, which equals 1800 kiloamps. Therefore, in this example, the panel AIC rating is 1800 kiloamps. Let's elaborate on these steps to provide a deeper understanding. When determining the transformer rating, it's crucial to accurately identify the kilovolt-ampere rating from the transformer's nameplate. This value represents the transformer's apparent power capacity, which is fundamental for subsequent calculations. For calculating the base current, the formula I equals kilovolt-ampere divided by the square root of 3 times primary voltage is derived from the basic power equation for a three-phase system. Using the correct primary voltage, either 480 volts or 240 volts, is essential for accuracy. When determining the maximum short circuit current, understanding the significance of the short circuit current at the primary of the transformer is important. This value represents the available fault current at the transformer's primary terminals and is typically provided by the utility company or can be calculated based on the utility's impedance. The transformer impedance, expressed as a percentage, reflects the transformer's ability to limit fault current. A lower impedance allows for a higher fault current. The formula SCC equals SCC multiplied by I calculates the short circuit current at the transformer's primary terminals, considering the transformer's impedance and the base current. When converting the primary short circuit current to the secondary short circuit current, the transformer turns ratio, TR equals secondary voltage divided by primary voltage, is used to step down the fault current from the primary to the secondary side. This step is crucial because the panel is connected to the secondary side of the transformer. When calculating the panel AIC rating, the panel safety factor, typically 1.25, is applied to ensure that the panel's AIC rating exceeds the available fault current. This safety margin accounts for variations in system impedance and potential increases in fault current over time. The AIC rating of the panel must be greater than the calculated available fault current to ensure safe operation during a short circuit event. Using the example provided, let's break down the calculations further. The base current calculation, 250 kV amperes divided by the square root of 3 times 480 volts equals 300 amps, determines the base current for the system. This value is used in subsequent calculations to determine the available fault current. The primary short circuit current calculation, 15 kA multiplied by 300 amps equals 4,500 kA, calculates the available fault current at the transformer's primary terminals. This value is then stepped down to the secondary side using the transformer turns ratio. The secondary short circuit current calculation, 4,500 kA divided by 480 volts divided by 240 volts equals 2250 kA, calculates the available fault current at the transformer's secondary terminals. This value is the available fault current that the panel will be subjected to during a short circuit event. The panel AIC rating calculation, 2250 kA divided by 1.25 equals 1800 kA, determines the minimum AIC rating required for the panel. In this case, the panel must have an AIC rating of at least 1800 kA to safely interrupt the fault current. Now, let's consider the importance of each step in ensuring electrical safety. Firstly, accurately determining the transformer rating is crucial for establishing the foundation for all subsequent calculations. An incorrect kilovolt ampere rating will lead to inaccurate fault current calculations and potentially unsafe conditions. Secondly, calculating the base current provides a reference point for determining the available fault current. This value is essential for understanding the system's capacity to deliver fault current. Thirdly, determining the maximum short circuit current is the most critical step in the process. This value represents the maximum fault current that the panel will be subjected to during a short circuit event. Underestimating the short circuit current can lead to catastrophic equipment failure and potential safety hazards. Fourthly, converting the primary short circuit current to the secondary short circuit current ensures that the fault current is accurately stepped down to the voltage level of the panel. This step is essential for selecting a panel with an appropriate AIC rating. Fifthly, calculating the panel AIC rating provides the minimum AIC rating required for the panel to safely interrupt the fault current. Selecting a panel with an AIC rating lower than the calculated value can result in the panel failing to interrupt the fault current, leading to equipment damage, fire, and potential injury. In addition to these steps, it's also important to consider other factors that can affect the available fault current, such as the length and size of conductors, the impedance of other equipment in the system, and the utility's available fault current. These factors can increase or decrease the available fault current and must be taken into account when selecting a panel with an appropriate AIC rating. Let's delve deeper into the practical implications of these calculations. When selecting a panel for a specific application, it's crucial to consider the available fault current at the panel's location. This information is typically provided by the utility company or can be calculated using the methods described above. The panel's AIC rating must be greater than the available fault current to ensure safe operation during a short circuit event. If the panel's AIC rating is lower than the available fault current, the panel may fail to interrupt the fault current, leading to equipment damage, fire, and potential injury. Furthermore, it's important to consider the potential for future increases in fault current. As the electrical system is modified or expanded, the available fault current may increase. Therefore, it's prudent to select a panel with an AIC rating that exceeds the current available fault current by a significant margin to account for future growth. In addition to selecting a panel with an appropriate AIC rating, it's also important to ensure that the panel is properly installed and maintained. This includes ensuring that all connections are tight and secure, that the panel is properly grounded, and that the panel is regularly inspected for signs of damage or deterioration. Proper installation and maintenance can help to prevent short circuits and other electrical faults, reducing the risk of equipment damage, fire, and potential injury. Let's consider some common scenarios where these calculations are essential. Firstly, when designing a new electrical system, it's crucial to calculate the available fault current at each panel location to ensure that the panels selected have an appropriate AIC rating. This is particularly important in commercial and industrial applications where large amounts of power are used and the potential for high fault currents exists. Secondly, when modifying or expanding an existing electrical system, it's important to re-evaluate the available fault current at each panel location to ensure that the panels selected continue to have an appropriate AIC rating. This is particularly important when adding new equipment or increasing the load in the system. Thirdly, when replacing an existing panel, it's essential to select a replacement panel with an AIC rating that is equal to or greater than the available fault current at the panel's location. This is particularly important when replacing older panels that may have lower AIC ratings than modern panels. Let's summarize the key takeaways from this discussion. Firstly, calculating the AIC rating for a panel starting at the transformer is essential for ensuring electrical safety. Secondly, the AIC rating of the panel must be greater than the available fault current to ensure safe operation during a short circuit event. Thirdly, the available fault current can be calculated using a series of steps, including determining the transformer rating, calculating the base current, determining the maximum short circuit current, converting the primary short circuit current to the secondary short circuit current, and calculating the panel AIC rating. Fourthly, it's important to consider other factors that can affect the available fault current, such as the length and size of conductors, the impedance of other equipment in the system, and the utility's available fault current. Fifthly, it's important to select a panel with an AIC rating that exceeds the current available fault current by a significant margin to account for future growth. Sixthly, it's important to ensure that the panel is properly installed and maintained to prevent short circuits and other electrical faults. By following these guidelines, it's possible to ensure that electrical systems are designed and installed safely and that the risk of equipment damage, fire, and potential injury is minimized. The accurate calculation of AIC ratings is not just a theoretical exercise, it has real-world implications for the safety and reliability of electrical systems. A thorough understanding of the principles and methods involved is essential for anyone involved in the design, installation, or maintenance of electrical systems. Furthermore, it is critical to stay updated with the latest versions of the National Electrical Code, specifically NEC Article 110.9 and NEC Table 310.15b16, and other relevant industry standards. These codes and standards provide detailed requirements for the selection and installation of electrical equipment, including panels and circuit breakers, and are designed to ensure the safe and reliable operation of electrical systems. Ignoring these codes and standards can lead to serious consequences, including equipment failure, fire, and potential injury. In conclusion, calculating the AIC rating for a panel starting at the transformer is a critical step in ensuring electrical safety. By following the steps outlined in this video and adhering to relevant industry codes and standards, it's possible to design and install electrical systems that are safe, reliable, and compliant with applicable regulations. A deep understanding of these concepts and a commitment to following best practices are essential for anyone working with electrical systems. Let's further discuss the importance of considering conductor impedance in AIC calculations. The length and gauge of conductors significantly impact the available fault current at a panel. Longer conductors and smaller gauge conductors increase impedance, thereby reducing the fault current. Conversely, shorter conductors and larger gauge conductors decrease impedance, increasing the fault current. To accurately calculate the available fault current, it's essential to include the conductor impedance in the calculations. This can be done using conductor impedance tables provided in the NEC or by using specialized software that takes conductor impedance into account. Neglecting conductor impedance can lead to an overestimation or underestimation of the available fault current, potentially resulting in the selection of a panel with an inadequate AIC rating. Another crucial aspect to consider is the impact of upstream protective devices on the available fault current. Fuses and circuit breakers located upstream of the panel can limit the fault current, thereby reducing the required AIC rating for the panel. However, it's essential to verify the interrupting rating of these upstream protective devices to ensure that they can safely interrupt the available fault current. Furthermore, it's important to coordinate the protective devices to ensure that the upstream device trips before the downstream device, minimizing the extent of the outage and preventing damage to equipment. Coordination studies are often performed to determine the optimal settings for protective devices to ensure proper coordination. In addition to these technical considerations, it's also important to consider the economic implications of AIC calculations. Selecting a panel with a higher AIC rating than necessary can increase the cost of the installation. Therefore, it's important to carefully calculate the available fault current and select a panel with an AIC rating that is adequate for the application, but not excessively high. Balancing safety and cost is a key consideration in electrical system design. Let's explore some advanced techniques for calculating AIC ratings. Software programs are available that can automate the AIC calculation process, taking into account various factors such as transformer impedance, conductor impedance, and upstream protective devices. These programs can significantly reduce the time and effort required to perform AIC calculations and can improve the accuracy of the results. However, it's important to understand the underlying principles of AIC calculations and to verify the results of the software to ensure the accuracy. Another advanced technique is to use per-unit impedance calculations. Per-unit impedance is a method of normalizing impedance values to a common base, making it easier to compare and combine impedances from different parts of the system. Per-unit impedance calculations can be particularly useful for analyzing complex electrical systems with multiple transformers and sources of power. Finally, let's discuss the importance of documenting AIC calculations. It's essential to maintain accurate records of all AIC calculations, including the assumptions made, the data used, and the results obtained. This documentation can be used to verify the safety of the electrical system and to support future modifications or expansions. Furthermore, documentation is often required by regulatory authorities and insurance companies. In conclusion, calculating the AIC rating for a panel starting at the transformer is a complex but essential task. By following the steps outlined in this video, considering the various factors that can affect the available fault current, and using advanced techniques when appropriate, it's possible to design and install electrical systems that are safe, reliable, and compliant with applicable regulations. A commitment to continuous learning and improvement is essential for anyone working with electrical systems.